Hello everyone, welcome to topic 1.3, elemental composition of pure substances. In this video we are going to address the essential knowledge parts where some pure substances are composed of individual molecules, while others consist of atoms or ions held together in a fixed proportions as described by a formula unit. According to the law of definite proportions, the ratio of masses of the constituent elements in any pure substance of that compound is always the same. So if it's sugar, it's always going to have the same ratio as other sugar substances. The chemical formula that lists the lowest whole number ratio of atoms of the elements in a compound is the empirical formula. So, going forward, let's look at these notes. So, a pure substance is one with constant composition. So, a pure substance can either be an element or a compound. So, that means that it's got the same look in the bottom of the container as the bottom or throughout the whole thing. When dealing with compounds, you can assume it follows the law of definite proportions, which states that compounds with the same elements in the same proportions are the same compound. They aren't magically different. Okay? Following the law of definite proportions, you can find the percent composition, which is the percent by mass, of each element that makes up that compound. To calculate the percent composition, you divide the mass of each element in a compound by the total molar mass. It is described by this equation where percent composition is equal to the mass of the element, which is the total mass in that compound. So mass of element total. So if there's a subscript, you need to multiply the periodic table mass by the subscript, and then here we have the mass or molar mass of the compound times 100, okay, because it's a percent. In compounds, the empirical formula represents the simplest ratio of one element to another element in a compound. The molecular formula represents the actual formula for the substance. The molecular formula can be the same as the empirical, but they are not always. Okay. An example is glucose, which has the molecular formula C6H12O6, but the empirical formula is CH2O. However, we're talking about the compound that is actually this one, where the empirical and molecular formula are the same. That's formaldehyde. Very different chemical properties compared to glucose. One you eat and it's food for your body, it's fuel for your life. The other is toxic and usually used for embalming. Don't consume formaldehyde. Thanks, guys. Okay, so to determine the empirical and molecular formulas, we have this procedure and process. I'm not going to go over it, but there are a couple key parts. One is that you assume that you have a 100-gram sample, so your percentages become the masses you work with. And then you do some molar mass conversions and do some whole number or division stuff to get whole number ratios. And then from that, if you're given, so to get the molecular formula, you have to be given the molar mass of the molecular formula. So we'll look at those here. Okay, so for our first in a certain sugar is used in treating patients with low blood sugar. And it has the following composition: 40% carbon, 6.7% hydrogen, and 53.3% oxygen. I'm going to assume two sig figs and that decimal place is missing, but we're going to divide by whole numbers, so it's not going to make too big of a difference. So it first asks us, what is the empirical formula? I'm going to focus on that bit right now. So we have 40% C, so we can say that that is 40 grams, that this is 6.7 grams, and this is 53.3 grams. So I'm going to take my 40 grams of carbon, my 6.7 grams of hydrogen, and this is a bunch of tiny space, but it was a PDF document. It was 53.3 grams of oxygen, and so I couldn't adjust the spacing. So if this is not enough room for you, you are free to use the margins or separate sheet of paper. I'm going to make this happen. So 1 mole of carbon has a molar mass of 12.01 grams. So I assume that the percents are grams, and then I'm going to change them into moles of each substance. So 1 mole of hydrogen has the molar mass of 1.01 grams hydrogen. And then for oxygen, 1 mole of oxygen has the molar mass of 16.00 grams. So I'm going to run that calculation for each one of these, and this is 3.33, this is 6.63, and then the last one is 3.33. So to reiterate, I take the percentages and I make them grams. I convert each one of those grams using molar masses from the periodic table into moles, and now I'm going to find the mole ratio between each one. How I do that is I'm going to divide by the smallest number out of my moles that I calculated. So my smallest number is 3.33. Yes, it's in 2 spots, but that's just luck. I'm going to always divide by the smallest one. So 3.33 divided by 3.33. The goal is that this sets one of them equal to 1 by dividing by the smallest. The smallest one is going to be 1. And that's as small as you can get in a compound's formula. Then everything else is bigger. And that is perfectly fine, and that is what we need. So these two are equal to 1, and this is equal to about 2. It's like 1.998 something, whatever, something. Like it's really close to 2. If it's not really close to 2, you then need to multiply and adjust the ratio. And I believe there is an example of that somewhere in your UDOs. Okay, so you don't round up unless it's very close. Cool? So then we have the empirical formula. These are our subscripts. So C1, H has a 2, and then O has 1. And we don't have to write the ones because it's implied by being present. Our second part of this question states that the molar mass of the compound is 180 grams per mole. So I'm given a molar mass for the molecular formula. It wants to know what the actual formula is. So to find the molecular formula, you must be given the molar mass of that molecular formula. You're going to find the ratio between the empirical molar mass and the molecular molar mass. So I need to know the molar mass of the molecular. So CH2O has 1 carbon, 2 hydrogens, and an oxygen. So I'm going to find their molar masses, multiplying by the subscript if I have more than 1. And I'm going to add them together. And for this, you should get 30.03 grams per mole. So now I'm going to use the molecular formula molar mass, 180 grams per mole. The bigger one should always go on top so you get a whole number. So we're going to divide these two to figure out what factor I need to multiply my empirical formula by. So 30 goes into 180 about 6 times. So I'm going to take my 6 and multiply it by to the subscripts in my empirical. So CH2O and multiply it to the subscripts. So that should be C6H12O6. And that is my molecular formula based off of the ratio between the molar masses of the molecular formula and the empirical formula. Okay, so for the we do, a compound is found to contain 56.5% carbon, 7.11% hydrogen, and 36.4% phosphorus. Find the empirical formula. Okay, so I want you to pause, but first remember that you take the percents and make them into grams, just as a hint. Okay, using the steps on the previous page in your notes and the example above, pause the video and try this one out. Okay, so you should see that by changing them into grams and converting them to moles, you get the moles based off the percent of each substance. Divide by the smallest that sets one of them to 1 and everything else bigger. You get their mole ratio in the compound, or the ratio of each atom in the compound. And so those become the subscripts. So we have C4H6P1, but we do not have to write the 1. Okay, so now using this, if the compound has a molar mass of 170.14 grams per mole, what is its molecular formula? I want you guys to pause the video and calculate this. The first thing you should do is calculate the molar mass of your empirical formula. Use the example prior and the steps in your notes to do this. Okay, so calculating the molar mass of the empirical formula, we should get 85.07 using the periodic table. Then using the given molar mass of the molecular formula, we're going to divide our empirical into it and we get 2. That is how much bigger the molecular formula is compared to the empirical. So we're going to distribute that 2 to each of the subscripts to get the molecular formula. Okay, so now complete the additional practice problems in the you-do. The answer key will be available for you to check your work in class. Thank you.